wanted to do is we wanted to sort of socialize some work that we've been doing at IBM with regard to what we call serverless operators, and I'll describe some more of that in a moment, but I want to start by just introducing myself. My name is Kyle Schlosser. I am a software engineer at IBM, and I've been collaborating on this work along with Andre Tost, who I believe has presented to this group in the past. He's sort of our overall technical lead for the software delivery of various IBM software services, and as well as partnering with other companies for workloads that run on Kubernetes. And another collaborator who's helped out in this space is Lionel Villard, who's from IBM Research, and he's in particular, he delivered into the Knative event source the capability of monitoring API resource modification events and generating cloud events from those in the Knative event style. So what do we mean by serverless operators? There's two aspects to that we're focused on. The first is scale to zero, which is effectively shutting down resources that are not being utilized so that we can achieve greater resource efficiency. In the broader scale to zero space, we also scale to zero also includes scaling up, but in the controller space, that's a secondary concern. We're also talking about event-driven programming. So this is more the traditional serverless, where you're trying to optimize, you're trying to achieve different programming models and simplify the construction of applications and react to events that are occurring rather than having these active server processes. And I'll go into more detail on what we're doing in each of these, but I did want to say that we're focused heavily on scale to zero, and this event-driven programming model is really, we're in the infancy on that. What we're doing there is we're trying to enable a future there. So we're working with the basic primitives there and trying to enable those to create the building blocks that we'll use in the future. So if we look at a typical controller, it's represented with this controller manager, which you see is the large box on the right side of this diagram. And within the controller manager, we have these source level components of reconcilers and the actual controller objects, and there could be multiple controller objects. But then when it comes to the actual processing of events, that's based upon these HTTP interactions back to the API server. First, to initiate like a long pole watch operation, and then wait for a response to that. And then, of course, when such an event occurs, then the reconciler component will react by perhaps making other updates to other resources and calling back to the API server again. So what happens because of that active state model, every controller has a slight overhead to it, and individually the overhead is negligible. So if we look at an individual controller that's, this is just an idle controller, it's been booted up, it's using 0.5% of the overall CPU of a single virtual machine, and 10 megabytes of memory are being consumed. But if we start considering running controllers where they're dedicated to individual namespaces, they're redundant, or they are scaled across like many different types of software, we can start to see that that aggregate effect have an impact on the overall capacity required in order to run all these various controllers. And a lot of controllers, in terms of the access pattern, they don't really need to be running all the time. So if we think about like our operators which bootstrap the platform, unless we are changing the platform after the fact, then we don't really go back and need to, we're not making a lot of modifications that controller needs to react to. So it could shut down in the meantime. So I mentioned this already. I won't go into further detail on that, but basically that slide was just talking about the aggregate effect of having a lot of different controllers up and running. So we have proposed two different technical solutions as for resolving like how we can achieve this serverless operator, serverless controller concept. The first is based upon Knative. And so what we've done there is, and I was saying one of our researchers has contributed to this, is that we developed a Knative API resource event source. So within the Knative architecture, we have Knative Serve, which provides scale to zero capabilities. So that's sort of a substitute for a deployment that's able to scale to zero. It'll scale up and down based upon traffic coming in. And then on the other side of that is the generation of events, and that's done through these event sources. And so by creating a Kubernetes API event source, we're able to combine the Knative eventing and Serve together into a full solution, which allows both scale to zero of controllers, but then it also enables, if you wanted to complement like an existing Knative application with incorporate Kubernetes API events into that application, then you can definitely do that. But then the second technical solution we have, and this is sort of a complement to the Knative solution. So without a dependency on Knative, now we can take an existing controller and scale it down to zero if there are no resource modifications of interest to that controller. And then if such an event would occur, it scales it back up again. And this controller zero scaler is simplified, so it doesn't have the Knative dependencies there. It just reacts to these annotations that have been attached to the controller. And so we'll spend a few minutes talking about the Knative, but more, I'm going to spend a bit more time on the controller zero scaler, in part because that's what I've been working on more recently, and so I have a running demo that I'll show you in a few minutes. Okay, so in the Knative, I've talked through this a bit already, but I'll talk through it again. With the Knative event source, there's two components. There's an event adapter, which you see on the left of the diagram, and then you have one or many of the receivers, which are the substitute for the traditional controller or controller manager processes. These on the right side, the controller manager has been reconfigured so that they accept cloud events. So cloud events is the transport mechanism for events within Knative eventing. And so we've had to slightly alter the controller process so that rather than reaching out, create a watch subscription against the Kubernetes API server, instead we wait for an inbound event which happens to come over HTTP, and then process those events by parsing them, unmarshalling them into the proper Golang data structures before sending them into the reconcilers. So we in the lab, we've prototyped this by adapting the controller runtime framework in order to accept cloud events. And then on the sender side, on the left side of the diagram, we have the event source, which consists of a Kubernetes custom resource definition within the Knative event source style. So basically there's a controller watching for these resources to be created, and the resource defines what API types we'd be watching for, and then it sends those off into an event sync. And the event sync is basically the transport that would go off to these individual cloud event receivers. So using that Knative eventing style, we've been able to successfully demonstrate controller scaling to zero and accepting events. But we also found some drawbacks in the process, and one of those is that we weren't able to quite achieve the scale to zero footprint optimizations we were hoping to. And this was a result of the event adapter. It's on the left side of the diagram. that was represented as an individual deployment, and we, due to the RBAC requirements or trying to provide independent RBAC isolation between different controllers, we ended up booting up an event adapter for every controller. So we didn't achieve a lower number of container processes being executed. So that's an area that I think we'll look at in the future in terms of how we can optimize that particular event source. We also have this dependency upon Knative, including specifics within the controller implementation. So we need to modify that controller implementation in order to accept these cloud events and to open up this additional HTTP transport. And so there were some additional requirements on the controller that we hope to eliminate. And the source code for that event adapter has been published, and it's actually been changed since we originally pushed the contribution. It's now found in the Knative eventing repository, and it's called the API server source. So if you were interested in programming to that event source, you can go out and grab the code. Although the last I looked, there wasn't a lot of examples, so you might have to wade through some of that. Okay, so the zero scaler then was the second technology second technical solution that we looked at in this space. And in the controller zero scaler, what we're trying to do is just shut down idle controllers. So we've tried to do this without any modifications or minimal modifications to the controller, so that existing operators could take advantage of this with little or no modification. And with this zero scaler, the way that it works is that the existing deployments or stateful sets are annotated with some information that is consumed by this secondary controller component. And that basically tells the overall controller which operators are interested in which events and which types from the Kubernetes API type system. In addition, there's an attribute called the scale timeout, which determines how long the controller is idle before we scale it down to zero. So like a typical use case that you might have is that as a Kubernetes operator provider, you could put some of the annotations onto your stateful sets or deployments. Those would just be ignored on systems where the zero scaler is not present. And then by letting you could also put the scale timeout on as well, or you could leave that to the cluster administrator. So when someone were to install your operator, then if they were to add this annotation with the timeouts, then that would actually activate the zero scale capability in the presence of the zero scale controller. And so in that way, you could sort of pick and choose or leave it up to the actual installers of an operator whether they would see that zero scale capability or not. Okay, so I mentioned this is driven by annotations. So the annotations are just added to that stateful set or deployment that's representing the individual operator. And then we have, in terms of the runtime, we have this controller zero scaler is the component name, but it itself is a controller that's watching for these different things to happen. So by scaling down these deployments to zero, if an individual operator or controller was expecting not to get scaled down, so like it has background activities it's doing, it's starting its own internal timers, this technology approach wouldn't really be suitable for that. It works for those controllers where they're responding to these reconciliation events. Eventually, they process the active reconciliations, and there are no more reconciliations that need to be processed. At that point, they can just basically be stopped. It also relies on the fact that most controllers predominantly will, on start, will reconcile those events or re-reconcile the current state of the resources that are out there. And so if you did have a controller that didn't meet that criteria, then it wouldn't work for it. Okay, so I've talked through this a bit more, but I'll show an actual example here. This is what you might see as the typical annotations. So there's 3 annotations that we're watching for here. The first represented here is the owned kind. So those are the types of resources that this controller owns or is creating and generating. The second aspect is the timeout, which is how long we're idle before the current controller will be shut down. And in this case, if it's idle for 10 seconds, it will be scaled down to 0. And when it's scaled back up again, the scale up is always immediate, so the timeout doesn't apply to scale back up. And then the last attribute is the watched kind. So this is the types of resources that this controller is watching for. In the case of my demonstration here, I'm using the Bonsai Cloud Istio operator. So it's watching for Istio types, and so that's what that controller responds to in its reconciliation loop. Then at the bottom of the screen, yes.
Can I ask a question in the middle? So
sure.
This is Stefan. So what would trigger the scale up again? So I couldn't get that. So for this scale down on timeout, yeah, I understand. But the scale up, is it then an external event, or if the
so what happens is for like the watched kinds or owned kinds, if there's no modifications to those, then the controller gets scaled down to 0. Yeah. If a change does occur to one of those, so in this case here, if the Istio resource is modified, then the controller will get scaled back up.
Okay, yeah.
And that scale down and scale up is orchestrated through what itself is a controller. And so we call that the zero scalar controller. Okay, so the annotations then, of course, in Kubernetes style can be either incorporated, into the application itself, or they can be annotated after the fact. And so at the bottom of the screen, I just have an example of what that looks like. Okay, so I'll show you the short demonstration here. So right now I have a brand new Kubernetes cluster. It happens to be Minikube. I just started it up. I haven't deployed anything onto it. And so I've got 2 components that I was going to deploy out. The first is the Istio operator. So this is just going to apply the various resources for that. And then the other component is the zero scalar controller, which I'm just going to be running actively. It's not going to be containerized. So that'll come up, should be up and running here. Okay, and then I'll start a watch so you can see that the Istio controller is in fact up and running right now. So at this point, it's just the Istio controllers, these 2 controllers are up and running, but nothing's really different in this system from if you just sort of go out and install the Istio controller. Okay, so the next thing I'm going to do then is to annotate that stateful set for the Istio controller. I'm going to use a 10-second timeout, which I think is probably shorter than what you would typically use in like a production case, but it works well for this demonstration. And then I'm just specifying which watch kinds are relevant to that controller. So that will be the determination of when the controller actually gets scaled down. Okay, so we've now annotated that controller, and so the 10-second after 10 seconds of idle, we should see that it scales down, and you can see that's starting to happen now. Scale down has been requested, but it hasn't been achieved yet. So once the full scale down has been achieved, you'll see 0 out of 0. And sometimes on a stateful set, that takes longer than on a deployment. Okay, in the meantime then, what I'm going to do is apply a sample document. And so we've now achieved full scale down to 0. And then as this document was created that triggered within the zero scale controller, even though the original controller was shut down, the secondary, this overall zero scale controller was watching for these modifications. That was based upon that annotation again, and recognized that a resource relevant to the Istio operator had changed, and so then it scaled it back up again. And you can see that it scaled it back up, but then now, since we're idle again for that 10-second window, we're getting to scale back down to 0 again. And so if we have another modification, it will again just continue to repeat that process. Recognize that something has in fact changed and scale it back up or scale it down if it's been idle beyond the timeout. Okay, so then just to wrap things up, with the zero scale solution, this is currently, it's just been developed locally. It hasn't been open source yet, but we expect to open source it within the next couple of weeks under the IBM namespace as controller zero scalar. And so that will be available shortly. And then, as I mentioned before, the Knative event source has already been open sourced and is being worked in the community, matured in the community. But then also on the Knative side, I think look for other future projects to come out as well that would further enhance that use model. Okay, so that's the end of what I have. But I would welcome any questions if you have any.
So how do you handle bursting? I mean, if you have a lot of requests coming in at the same time, you're going from 0.
Yeah. So the
kind of idea. Go ahead.
Yeah, there's the Knative event source controller would handle that a bit better. Is that you could specify parameters of how high you wanted to scale it up. The zero scale controller doesn't handle that case right now. It's just scaling it up to 1. That's a feature that we would need to look at implementing is a way to handle that.
Anyone else with questions or other topics you want to talk about?
This is Michael from Red Hat. Just wanted to add that presentation was super cool. I've been really interested in that topic for the last few months and just haven't been able to carve out any time myself to really take it seriously. So it's actually really great to see that you guys have dug so deep already on this and are going to keep going. So I'm looking forward to seeing when you make that available for the rest of us to look at. Thanks.
Anyone else with either topics? I mean, again, I echo the notion here that this is very interesting and absolutely needed. So. Cool. Well, if that's it, then I guess we all get about half an hour back of our day. Thanks again, Kyle. This was a very good presentation, and